Hello everyone, my name is Aryan. I'm 13 years old. I'm studying in 8th grade, and for today our topic would be about supersymmetry. So, introduction to supersymmetry. So, it is a theoretical framework that extends the standard model of particle physics. It proposes a symmetry between fermions and bosons, two fundamental classes of particles. Despite its success, it is still an effective theory and valid at only certain scales. So, what it does is that if we have a quark, so it then will become a squark. So like the quark is then matter, right? And its counterpart would be a force. So then the squark, then the squark would be an boson. So the squark would be an boson and it is a counterpart of the quark. These are called the supersymmetry particles, and most of them are very heavy, and the quark and the squark is about almost 1,000 times more massive, like heavier than a normal quark. So basic concepts of supersymmetry. Supersymmetry introduces superpartners for each known particle differing by a unit by half a unit of spin. These superpartners are called sparkles and include particles like electrons and quarks. The symmetry implies a deep relationship between the forces and matter particles in the universe. So this naming root, the if we convert a quark into a super symmetry particle, then we will add a s into it. And if we have to like do it with a force, like and in Higgs, so it will we will add I and O to the back. So this is the naming rule in supersymmetry. Lorentz invariance. So it is in deep symmetry of space-time. It says that the laws of physics remain the same for all observers moving at constant speeds relative to each other. It forces the speed of light to be a universal constant. Lorentz invariance ensures physical laws remain identical for all observers regardless of velocity or orientation, cementing the universal speed limit. So it is like a symmetry. Symmetry isn't just about things looking the same. It is the reason laws exist in the first place. So Satyajit, have you heard about Noether's theorem?
No, I don't recall anything specific like that.
So Noether, she's a well-known female scientist. So she pointed out a mistake of Einstein's special relativity energy conservation rule. It contained a pseudo tensor. So what she did, that she proved Einstein wrong, and in doing so, what she did, that she just proved that why do laws even exist? Why do these conservation laws exist? And I think so. It's a pretty deep concept. It contains like empty universes and other things. So this explains, her theorem explains why do conservation laws even exist. So Noether's theorem also states that every continuous symmetry in nature corresponds to a specific conservation law. The laws of nature must be the same regardless of where or when you perform an experiment. So there are local symmetries also that we have discussed in our previous presentations. So we'll talk about them later. So, and these things lead to the fundamental conservation laws and this Lorentz invariance. So it is like a mathematical core concept of special relativity. So supersymmetry transformation. So the supersymmetry transformation utilizes a mathematical operator to exchange fermions, matter, and bosons forces by shifting particle spins by one by two. It predicts superpartners for every known entity. This symmetry implies matter and forces are just manifestation of one framework, fundamentally linking internal particle properties to space-time geometry. So this is well explained in superspace. So superspace is like a 4D graph. So we'll talk about that later. And in the supersymmetry transformation, it has a mathematical operator. So there is also some flaws in it. But what this does is that it exchanges the fermions, matters, and bosons into their counterparts. Like if it is a matter, it will become into a boson, and it shifts and particles spin by one by two. So, ladies and gentlemen, any questions? Satyajit, do you have any question? Okay. Hello, Satyajit.
Yeah, you said hello.
Yes, Satyajit.
Yeah, so you said it predicted superpartners for each for every known entity. What does entity signify here?
Okay, so entity, so it signifies the fundamental particles like the top, the quarks, the electrons, these types of stuff. So, did you get me?
And what does superpartner means here?
So a super partner means that if I have a quark which is matter and its super partner would be a boson, which is which is a force. But there is one more thing there that this like it's still the boson, the super partner of a quark, which is called a quark, is pretty heavy and it does not do like pretty much of anything. We haven't also discovered them. These are still you can say hypothetical, but this theory is pretty successful. Okay, explain it again. Okay, so Satyajit, did you get this one? What was I trying to say?
So the bosons are hypothetical, or the partnership between the boson and the quarks?
Okay, so the supersymmetry predicts that these super partners are there, but we haven't discovered them. But these do help us a lot uh, in explaining many problems of it. Of physics. So we'll talk about these. There is one hierarchy problem here, which is explained by supersymmetry pretty beautifully.
Are we
So
already working with the bosons? The boson particles are those are hypothetical as well.
okay, so the boson particle is real, but there is one just a little problem. It is supposed to be like about the limit, like the Planck limit, which is about 10 raised to the power of 19 giga electron volts, but it is pretty light, but it is still pretty heavy compared to a proton. So this mass issue, to figure this out, supersymmetry gives us a pretty good answer. So we'll discuss that in the presentation. So did you get me?
Yes, yes, continue please.
Okay. So I think so. Someone said to explain it again. The supersymmetry uh, transformation. So in supersymmetry, there is a mathematical operator. It looks like a little bit of a Q. So what it does is that it changes a matter particle into a boson, which is a force, and it what it does with the particle is that it subtracts about exactly half units. So that is the supersymmetry translate mathematical operators. So it changes the force into matter and vice versa. So that happens. and the super partners of each quark or others are very heavy than the original ones, like the electrons, quarks, etc. Motivation for supersymmetry. Supersymmetry helps to stabilize the Higgs boson mass against large quantum corrections. It provides candidates for dark matter particles such as Neutralino. Supersymmetry can unify the fundamental forces at high energy scales, suggesting a grand unified theory. The hierarchy problem. The hierarchy problem concerns the large disparity between the weak and the Planck scales. So it provides a mechanism to cancel quantum corrections that destabilize the Higgs mass. It offers an elegant solution to maintain the stability of the electroweak scale. So we can see in the picture that there is the Planck. So it is about 10 raised to the power of 19 giga electron volts. So like one more thing about the Higgs boson is that it also has mass. It is about 125 giga electron volts. So it is pretty like it's the heaviest elementary particle that we ever know of. So but what happened that our calculated mass should have been 10 raised to the power of 19 giga electron volts. But what happened that when the Large Hadron Collider discovered that the Higgs boson is about only about 10 125 giga electron volts. People were very much confused, and this is where supersymmetry comes and solves these issues. So one more thing, that the Higgs boson is a scalar particle. So scalar means that it has no spin. And okay, so the mystery is that this boson, Higgs boson, is too light because mathematically it is incredibly sensitive to the highest energy level scales in the universe. And if the standard model to were the complete story, every particle like it interacts would act like a weight pulling its mass upward during quantum fluctuations. So this is where the virtual particles and other things come. So the Higgs field, if we strike it very hard, what happens? That we get a Higgs boson, which we'll get a Higgs boson, and this does not have any spin. So so its spin is zero. So it is prone to some things. So what's the case that in the vacuum there are virtual particles forming, and like they pop in and out of existence, and the heaviest ones are the top quarks. So whenever a Higgs boson is there, as it moves, it interacts with these top quarks and other quarks, and there is one thing called quantum loops. So this majorly happens from very heavy particles like the top quark. They naturally drive the Higgs mass to the Planck mass limit. Like every time the Higgs boson collides into a particle like a top quark, it gains a little bit of mathematical weight. In the quantum world, there are billions and trillions of these top quarks popping in and out of existence. So it means they should be constantly bumping into the Higgs, piling up on so much weight that the Higgs becomes trillions of times heavier than it actually is. In the quantum world, there are billions of these popping in and out of existence. So they should make the like this Higgs boson pretty heavy, but it does not. So, uh, so ladies and gentlemen, any questions? Satyajit, Satyajit, what's the question?
So you mentioned regarding the energy level sensitivity of Higgs boson, stating that they are very high, right? So my first question would be, in matter like let's say atom, the only thing that is affected by energy levels is the electrons, and it doesn't affect really much towards the nucleus. Is this a fair statement to make?
Okay, so you're saying that these energy levels only affect electrons. So I think so that okay. So I think so that should be correct. I don't think so. I got your question pretty well.
So it's basically the sensitivity to the energy levels is shown by only electrons within an atom, or is it the nucleus as well?
Okay, the nucleus. So
Because upon seeing the electrons, we can say if an electron is in high energy state or low. But can you differentiate between a nucleus of a high energy atom and a low energy atom? That's the question.
low energy atom and a high energy atom. Okay. So I think so. I think so. One we can differentiate them between. There's one concept called nuclear bonding in an atom. Uh, it depends on how. I think so. It depends on the number of particles in an atom. I think so. One way to differentiate them would be this, and the protons and the neutrons in the what you can say the the atom are most majorly not affected, but if they come very close, they there then the new quark deconfinement can happen, and they'll get aseptic freedom, which means that their quarks can move freely now. So I think so. This can be one of the way to differentiate them.
So would this change come along with the change in the energy levels? And the thing that you mentioned regarding the number of particles and the bond, the nuclear bond, with the change of with the change of energy levels, we don't see any change in the number of particles, do we?
Yes, that.
So that cannot be one of the things that you can look for.
So I think so. The only way a proton can be energetic if we if we accelerate it to very high speeds. So I think so that is the only way.
So what would then happen? How would
Since
speed differentiate it?
like uh, if two very high energy protons collide, they can send a ripple in the Higgs field, which it would be like throwing a pebble at the ocean, and then we will see waves and ripples. So that waves and ripples give birth to the Higgs boson. So it's a part of the uh, Higgs field.
Won't this thing happen if we consider two highly energetic electrons
Yes,
or say neutrons?
electrons and neutrons. So okay, I electrons would they will just repel each other. If I don't, I don't have any idea. I'll tell you later if I got the answer to it.
Okay,
I'll
sure.
wonder about this. Okay, I think
So
so. Do you have any other questions?
yeah, there is a second part to it. That is basically, let me recall. Okay, you can continue. If I recall, then I will just
Okay.
tell you.
So let's move to the topic, the mystery of the Higgs boson. So the Higgs boson is too light because mathematically its mass is incredibly sensitive to the highest energy scales in the universe. If the standard model were complete story, every particle it interacts would act like a weight pulling its mass down upwards, uh, its mass upwards during quantum fluctuations. Quantum loops from heavy particles like the top quark should naturally drive the Higgs mass towards the black mass. So, did everyone get why should the Higgs boson be heavy? Did everyone get that? Why should the Higgs boson be heavy? Someone, Rakshit Ranjan has said yes. So thank you, Rakshit, for joining us. If you have any questions, you can raise a hand and ask us. So I think so Satyajit, you are trying to say something.
Yeah, you said it was light, right? Because you said it should be 10 to the power 25, but it turned out to be 10 to the power 19.
No, you got them wrong. It is supposed to be 10 raised to the power of 19, but it is 125.
Okay, so it was found to be heavier.
Yeah. Yes. So do you know why it is supposed to be heavier?
No, can you just repeat it?
So you know someone someone is asking some questions. Can I ask questions related to space science? So I think so. We'll do that at the end of the presentation. We'll first do the topic first. So Higgs boson should have been heavy because you know that there are virtual particles popping in and out of existence. So there are some heavy ones like the top quarks. So what happens that the Higgs boson has no spin. So it has no spin, and there is one. So is one thing called quantum loops. So what happens that just has the top quark interacts with the Higgs boson, which has no spin. What would happen that it would give uh, some mathematical mass, a weight to it. So, and there are trillions and billions of these top quarks popping in and out of existence in just like a very small space. So mathematically it should have gone to the Planck mass, which is like a trillion times trillions and billions of times more massive than its current state. So did you get me?
But you mentioned at the start of the presentation that the Higgs bosons are nothing but a form of energy and not like the matter.
Not a Higgs form. No, I think so. Can you repeat yourself? Higgs.
So you mentioned that unlike matter that have quarks, you said that Higgs bosons are basically a form of energy.
No, I okay. So I think so. I was talking about the super partners. So there is matter. There are fermions, and if I want to convert them into the forces, the bosons, what will I do? Is that I will just add a s into it. So quarks to squarks. It was the naming rule. I was explaining the naming rule of this supersymmetry. I think so. You heard it wrong.
So the boson and the Higgs boson, you are treating this as different.
Okay, so there's a difference between a boson and a Higgs boson. But there is one similarity that they both have zero spin.
And the form of energy is the boson, I guess.
Okay, so like boson is the force carrier. So there are force carriers to light, which is the photon, the weak nuclear force, and the nuclear forces, the gluons and the other things.
So the bosons are not equal to quarks, right? Not they
Yes,
do have quarks.
So, but in supersymmetry, they have super partners which have zero spin and they are considered bosons, but they like are not force carriers. So this is also the case for mesons. They are not force carriers, but they have zero spin. That's why they are considered bosons.
So they do have quarks or not?
So they do have quarks. They are, I won't say quarks. I would say squarks. They are the super partners of quarks. So that's why they have an S in front of them.
Okay, so the boson is not a fundamental particle. Is that what you are agreeing?
No, it's not a particle. It's, let me say that it's a force carrier. But in supersymmetry, we considered that these things, the super partners, are real. So so we can say that in the supersymmetry, there are more bosons in the supersymmetry because we considered them.
Yeah, but you must include that in either of the two sections. It's either the particle or is the force. So you are
Yes.
saying it's neither of them.
So no, it's so a boson is in the category for force carriers, but it has also the mesons, which are also not a force carriers, and they are considered bosons in the standard model of physics. But in this supersymmetry, we got more things like the mesons, which are also not a force carrier.
So there are things that are not particle but not as well forces.
No, you got it wrong. These are particles in, they're considered to be particles in supersymmetry, and they have mass, like they have a lot of mass than the regular quarks and these stuff. So they are particles.
But not matter.
Okay, so these are, so but not matter. I did not uh, get the context of. Can you?
So we have a specific definition tied to matter, right?
Yes.
So first of all, would you consider photons as matter?
Okay. So okay. So these would be just like these would be just like the quarks, but in supersymmetry they have some other properties which make them helpful for this hierarchy problem.
No, the question is simple. Would you consider photons as matter?
Okay, would I consider photons as matter?
Yeah.
Okay, I don't. Okay, of course, they don't have mass to them, but would I consider them a matter? Okay, I think so. I should. They exist. Uh, Forces, mass, and
If one thing is not a matter, that doesn't imply it should exist or not, because forces on the other hand we have that are not matter, but they do exist.
okay. So, Satyajit, did you get this hierarchy problem and
Yes,
why this Higgs boson should be heavier, but it is not?
yes, I did get that.
So, okay. Why should the Higgs boson be heavy? In the quantum world, the Higgs boson does not exist in isolation. It is constantly surrounded by a cloud of virtual particles like top quarks that pop in and out of existence because the Higgs is a scalar field, a scalar particle, which means that which means it has no spin and it is uniquely sensitive to the masses of these neighbors. So it means that if it interacts with a top quark, what would happen that what would happen is that the top quark would give it some mathematical weight to it. So that is why they are supposed to be heavy. And so, Satyajit, I have a question for you. The Higgs boson is supposed to be heavy, but it is light. So, do you have any guesses on how is that?
You just said it, na, it has some mathematical mass associated to it, for which it was thought to be light, but it turned out to be much heavier.
No, you got. I think so. What was I saying to say? Uh, is that whenever the Higgs boson moves, it interacts with the virtual particle called these are like top quarks which pop in and out of existence, and because it is a scalar particle it has zero spin. So what happens that the top quarks gives it some mathematical mass, and there are billions and billions of these top quarks popping in and out of existence. So it means that the Higgs boson should be very heavy, now not 125. And so but the observed was very less. So do you have any guesses on how is that?
And
Okay, so Satyajit, what were you saying?
I would guess that upon interaction further in the physical world, they might be releasing some mass. That's my guess. I don't know.
Okay, they do not release any mass. It has to do something with the supersymmetry, or in more general, they have to do something with the super partners. So as we discussed that these virtual particles come in and out of existence like the top quark, so there is an anti-top quark. So these you can call them the stop quarks, the super partners of top quarks. They also come in uh, virtual pairs. So it is the twin, is this twin of the top quark, and it pulls the mass of the Higgs down. So can you imagine the whole Higgs boson mass is like a tug of war, and there are equal players and on both sides, and each player is pulling the same. So the top quark is helping the Higgs boson be heavier, but what's the stop quark doing? It is pulling the mass of the Higgs boson down. So did you get what was I trying to say?
Well, did you just associate the same quark with both increasing the mass as well as dragging it down? The
Yes,
top, the top quark you said earlier was responsible for having the mass
yes,
increased.
yes, and one more thing that the stop quark, the twin of this stop quark, pulls the mass of this Higgs boson down. So,
No, I don't get you. What drags it down?
uh, can you repeat yourself?
What drags it down? I don't get the exact word you used for it.
The stop quark. So, like, it is the super partner of this stop quark,
Okay, the super partner for of this
top
top
quark.
group. Okay.
So, so it's pretty amazing, right? There are so many particles, top quarks, and there are the same number of stop quarks which are doing the opposite of the top quarks and maintaining the Higgs boson's mass at the same level. Okay, so the mathematical foundation of supersymmetry. So it is based on a set of mathematical operators called supercharges that relate bosons and fermions. These supercharges extend the Poincare algebra, forming a superalgebra. This algebraic structure ensures the invariance of physical laws under supersymmetric transformations. So it also has a mathematical operator which changes the matters into the bosons. It looks like a little bit of like cube, supersymmetric particles and their partners. So each standard model particle has a corresponding partner, quarks with quarks, leptons with leptons, gauge bosons like the photons have fermionic super partners called photinos. The Higgs boson has a fermionic partner called Higgsinos, completing the super multiples. So the bosons, like the photons, have the fermionic superpartners called photinos, and the Higgs boson has a fermionic partners called Higgsinos. So, so a supersymmetry also helps us do this hierarchy problem, and it is also a contender for dark matter. So there is the force, I am forgetting its name. Uh, it is an so so there's a neutrino, we all know. So there is the neutrino. It has an I and O at the end because it's the super partner of this neutrino, and it is supposed to be heavy because the dark matter, it's a very pretty heavy particle, and it does not interact. It has electrically no charge. It only interacts by the weak nuclear force and the gravity. So so that's uh, that's uh, that's how supersymmetry helps us, uh, and also gives us a contender for a dark matter. Fine tuning. It's the mathematical mystery where the Higgs boson's mass appears miraculously light. Theory predicts its quantum corrections should drag its mass to the massive Planck scale to match reality. Independent numbers must cancel out to 34 decimal places. A coincidence so unlikely physicists see supersymmetry to explain it. Supersymmetry breaking. Supersymmetry must be broken because superpartners have not been observed at current energies. Breaking mechanisms include gravity meditated gauge meditated, and anomaly meditated models. The scale of supersymmetry breaking determines the masses of superpartners impacting their detectability. So, so a supersymmetry breaking. So it does break. It's still a pretty effective theory, but it is only valid at pretty certain points. And supersymmetry breaking is the thing, like it's the thing that we are still alive, and uh, the protons have not decayed yet. So it's the reason for that. So, okay. So uh, the protons decay. So if like in the quarks, a proton does not have a super partner because it's not an elementary particle, but the quarks in them, if our universe had followed supersymmetry, a quark would have had a squark, and because if the supersymmetries was not broken, the protons would have decayed, and it's also one of the reason the super partners of the quarks electrons are way heavier than those of the normal particles. In a universe that is following supersymmetry, what would happen that physics would treat these two as this independent and the same. So it means that this also one thing. This is also a force meditator, that the S quark. So it would give us a way to make that quark into a pion and a neutrino. So which would mean that the protons quarks have decayed. So, and if that happens, what would happen that there would have been no, the universe would have no structure because protons would just decay. So why is that not happening? Because our universe is breaking this supersymmetry. So there is one a topic called the R-parity. So this is the reason our universe is still alive. It forbids these types of decays. It forces superpartners to be only created and destroyed in pairs, which mathematically blocks the path that would lead to the proton's destruction. So it ensures that a normal quark like a top quark cannot suddenly change into its superpartner, a stop quark, while it's zipping through space. If that happened, the R parity would flip from minus plus one to minus one, which is forbidden. So like the normal matter have plus one R parity, and the partners have minus one. So to maintain R parity, what happens that these come in pairs. So minus one times minus one is equals to one, and a normal particle cannot turn into a super partner because if it tries to like 1 times 1 it would be just 1, not a minus 1, and the minus 1 is for the what we call the super partners. So ladies and gentlemen, do you have any questions? Satyajit, did you get this? What was I saying?
Yes, I did, but does that imply that in order for the existence of a particle, all its superpartners should not exist simultaneously?
Okay, should not exist simultaneously.
Because if they do, then it just would annihilate, right?
Okay, so let me say that these two are different families. The S quarks and the quarks. These are different families, and
Okay, so the same one can be simultaneously present. Like you mentioned, minus one and minus one can indeed be present. That goes for minus two and not just zero, as it happens in minus one and plus one.
okay. So what? So R parity. So the minus one I just said is for the super partners. So to conserve this uh, R parity, what happens that they come in pairs. So minus 1 times minus 1 is 1, and a normal, okay, so and normal 1 and normal matter is just 1. So I think so you were trying to say that normal matter cannot turn into the super partners. I think so that's what you were saying, right?
Yeah, I was just saying that if the superpartners are opposite in nature, then they would just annihilate if they tend to be in the same time.
They would annihilate. Okay, I haven't heard about that annihilation. The
So are these equal in nature, or I was assuming they are in opposite nature? Like we have neutrons, we have protons, and the other particle. Are they not within supersymmetry? Are they not superpartners?
Okay, so they can. Okay, I don't think so that they. Okay, I don't think so. These super partners uh, like interact with each other. What happens is that they decay into lighter and lighter particles. So if it is a stop quark, it will then decay into the other things, and then it will reach the lightest super symmetry particle, which many theories believe is the neutrino, uh, which is the super partner of a neutrino, and that is like one of the reason our protons do not decay. So and so these super partners do not actually, they can't interact with each other and annihilate each other. They decay into smaller and smaller or lighter and lighter particles by emitting some energies. So
So a positron is a pair of what?
A positron is a pair of what? Okay,
The opposite pair of what? Is it a proton or electron? What was that?
okay. No, I think so. You misheard. It was neutrino.
No,
So
it's one of the assumptions that I am taking. I just want to clear it up. So the positron is a pair of what particle? What is the opposite of positron?
okay. So wait. Uh, is it a matter particle? I
Yes, it's a fairly simple one that don't just associate it with this topic. A positron is a opposite particle of what?
positron. Okay, so its super. Wait, its super partner would be so. Its super partner would have an.
No, I'm not asking about the super partner. That would be my second question. So what
Okay.
I'm trying to ask is, as you had mentioned, there are antimatter partners for the matter partners. So for
Yes.
like if we take electron, then what would be the opposite? I mean the antimatter part of it.
Yes. Okay. I did. Okay. So so they. Yes. So you are right. They come in pairs. If there's an anti-stop quark, there would be a stop quark, and I haven't heard about them destroying each other. They decay into lighter and lighter particles. That's
Then okay, okay.
okay. So one more thing that like a stop quark would decay into a lighter particle, and then it would go through a chains of decays, and what would happen that it will become the there is a particle called as the LSP, lightest supersymmetry particle, which is thought to be the super partner of a neutrino. So that is why the protons do not decay. And okay, let's just get to the topic right now. Experimental searches for supersymmetry. So particles like the particle colliders, like the Large Hadron Collider, actively search signs of superpartners, signatures including missing transverse energies and events with multiple jets and leptons. So far, no conclusive event evidence for supersymmetry particles have been observed, setting mass limits. So one more reason can be is that like there are like about 1,000 times like S quark is about 1,000 times more massive than a regular quark, and that can be one of the reasons we haven't been able to discover it. So challenges in detecting supersymmetry. So compressed spectra can make superpartners difficult to distinguish from background noises. The large parameter space complicates targeted searches and interpretations. So this non-observation of this supersymmetry challenges this fine tunneling and many other things. Okay, implications of discovering supersymmetry. So confirming supersymmetry would revolutionize our understanding of particle physics and cosmology. It would provide a natural dark matter candidate and support a grand unifications of theories. The discovery would open a new window into physics beyond the standard model. Okay, so it is also present in string theory and quantum gravity. So, supersymmetry is a key component in superstring theories, unifying gravity with other forces. Superstring theories require supersymmetry to be consistent and anomaly free. This connection between supersymmetry is fundamental to a complete theory of gravity.
यूएसए वाले ज्वाइन करने के लिए बोल रहे
Okay,
हैं अरे
okay.
बहुत फ्लो हो गया
So, dark matter and supersymmetry. So supersymmetry naturally predicts weakly interacting massive particles. The lightest
वो तो हम लोग
supersymmetric
के 10
particles,
मिनट में ज्वाइन करते हैं
LSP is a prime dark matter candidate. Experiments aim to detect these particles directly or indirectly through astrophysical observations. So in supersymmetry, there are many things. There are many supersymmetric particles, and one of them is the neutrino, which is called the which is the LSP, the lightest supersymmetric particle, which is like a prime candidate for dark matter because it is a weakly interacting massive particle. It is pretty massive, as all of the supersymmetric particles are, but it is also electrically uh, neutral.
आर्यन क्लोज करो, यूएसए के साथ मीटिंग होने वाला,
Okay.
बात करो।
Okay, so super space. So super space extends our four-dimensional universe by adding quantum dimensions. So these are also called Grassmann coordinates. This mathematical framework merges fermions and bosons into an entity called superfield.
बोलो।
By viewing matter and forces has different orientations with this. Is there? Okay.
वो बोल रहे हैं कि दूसरी जगह कोई मीटिंग अरेंज होने वाला, जल्दी ज्वाइन करो। बोल दो
Okay.
ना कि आई कैन ज्वाइन आफ्टर आई हैव अ मीटिंग इन यूके साइंटिस्ट
Okay, I think so. Everyone, I think so. I need to leave right now because there is one more meeting that I'm going to be in.
यूके
It's in it's organized by some people in UK, so I need to leave. I will join like after 10 to
10-15
10 15 minutes. So
थैंक यू सो मच फॉर
everyone, thank you so much for joining us. I need to leave right now. So Satyajit, I have to leave. There's